Welcome back, everybody. This is the last recording video for Stats 1. So congratulations, you made it. We are going to talk about contingency tables. We have seen contingency tables before, and what we're going to compare right now is how happy you are in your life right now and how is your current health. And what we want to do is see if these two things are independent of one another or not. So are they related or are they dependent on one another? So suppose you survey 2,000 individuals by giving them the questionnaire below. And actually above the, are you happy and how's your current health? Now you'll notice I don't have any values in here. All I have are the row, which are left and right, and the column totals. That actually is all we are going to need for this. We are going to be using a chi-squared test, is what it's called. And this is a test for independence. And so does health have anything to do with being happy? Or are they independent things? Now you can see the grand total over here is the 2,000. And so how many people are pretty happy? 1,098. How many people are in good health? 935 total. So we're going to use this table to answer the following questions so we can get an idea. We are going to be using our test statistic is again chi-squared equals equals the summation again of O minus E, the outcome here again. But as of now, we don't know how to find the expected value. We're only going to have the outcome values as we're looking at this. So we are going to try to calculate that out. Keep in mind that the expected outcome is n times p. So we're just keeping that in the back of our minds as we're doing this. And we're going to have to build up our probability. So I'm going to start with the probability that you randomly select an individual from the study and they are pretty happy. So all right, I'm pretty happy. So I'm going to go to the end of pretty happy. That's 0.98 out of the 2,000. Basic probability stuff here. What is the probability that you randomly select an individual from the study and they are of fair health? Well, how many people are in fair health? That's 405 out of the 2,000. So if they are independent, then how do we find the probability of pretty happy and fair health? So the probability, pretty happy, and fair health. That's going to be the probability of pretty happy times the probability of fair health. So that is 1098 over 2,000 times 405 over 2,000. So this is our probability of pretty happy and fair. Given the probability, about how many people from your 2,000 sample can you expect to be pretty happy? So remember, our expected is equal to n times is the number of people is n times p. Well, n in this case is the 2,000. P is above. I'll highlight it. This is your p. So we have 1098 over 2,000 times 405 over 2000. And you'll notice very nicely that reduces out. So the expected value is going to be 1098 times 405 over 2000. And that is our expected value, specifically up here, pretty happy and a fair health. That's going to be the 1098 times 405 over the 2000. That's our expected value. And we're going to have to do that for every single one of these categories, this 3x4 setup here. So let's generalize this. So in general, we would say that the expected value is the row total times the column total over the grand total. For each of these. So we would have to do its expected value for each and every single one of these. So that would be 12 slots that we would need to fill in. But don't worry, our calculator is going to do all that heavy lifting for us. All right, let us jump into some definitions. A little late on this one. This is a contingency table. Contingency table is a table consisting of frequency counts of categorical data corresponding to two different variables, which we just used, the health versus the what was it? Health versus happiness. That's right. And in a test for dependence, we test the null hypothesis, that is in a contingency table, and the row and column variables are independent. That's what we're testing for. All right, let's keep going. The data, sample data must be randomly selected. They are represented as frequency counts in a two-way table. A two-way table is another name for a contingency table. And E is at least 5. All right, here is our big ones, our null and alternative hypotheses. All right, here. Once again, here's our test statistic. Same test statistic as the goodness of fit, I should say. And E, again, is the row total times the column total divided by the grand total. And here's another new one for us, are the degrees of freedom. It's the number of rows minus 1 times the number of columns minus 1. And let's get some of these letters defined for us. So O represents the observed frequency. That will be given to us. E is going to be the expected frequency. R represents the number of rows, and C represents the number of columns. Now, to be clear, rows are always left and right, columns are always up and down, and the order always goes row, then column. So if we go back to our contingency table here, this would be a 3x4 contingency table, meaning 3 rows, 4 columns. And in math, that's a general rule that stays about the same. All right, let's jump into some examples. So, type of machine. A medical researcher wishes to determine if the type of vitamin pills, medicine, pardon me. A medical researcher wishes to determine if the type of vitamin pills taken is related to the age of the person. The data are shown below. We have our alpha, 0.01, is a type of vitamin related to the age of the person taking the vitamin. And we're going to use the p-value method to do this. Okay, so here we have the data. And so we would say that someone who takes a tablet and is between the ages of 40 to 59, there are 24 of those people. All right, what we're going to have to do is we're going to have to use a matrix. Let's get our null hypothesis out of the way first. So the type of vitamin pill is independent. Will be your pop-up menu of the age of the person taking the pill. This is not the claim. The claim is that it is dependent. To the age of the person taking the pill, and this is the claim. And okay, so now we have to figure out how to get this data. Now, we're not going to use the list function in our calculator. We're going to use a brand new function that you may have never used before. We are going to use the matrix function. This is going to be a 3 by 3 matrix. Now, that means that there are 3 rows and 3 columns. In fact, 3 rows, 3 columns. So our degrees of freedom is 3 minus 1 times 3 minus 1. That's 2 times 2, which is 4. All right. Once again, we're going to use the matrix function on my calculator and most likely on yours. It's the left column of buttons. And I'm going to go down. So you see the second, the alpha, below that is math, and below that is x to the negative 1 power, and above it is blue on mine. Yours may be a different color. It says matrix. So I'm going to hit second and then the matrix button. And here are the matrix buttons. So I need to go over and I'm going to edit matrix A. I need to redimension this as a 3 by 3 matrix. And now I'm going to just put the data in there. 8, enter, 12, enter, 17. Notice it doesn't matter if there's old data in there. I'm just going to replace it anyway. 17, 24, enter, 8, enter, 5, enter, 12, enter, 6, enter. All right, we have our data. We are ready to go. Let me quit out of that. And now, once again, we are going to run a chi-square test. I'm going to go to stat tests. Let's scroll down towards the bottom. And there is my chi-squared test, C on mine. So I'm going to hit enter. Now, here's the nice thing. The observed is what we have in our contingency table here on the left that I put into matrix A. The expected, remember all that work we had to do? The row total times the column total divided by the total total. They are going to calculate all of those for us in matrix B. I want to do one for us before we calculate this out so we can check it. So let's do row 1, column 1. So that's going to be 2037. So this is the expected value of row 1, column 1. So 8 plus 12 is 20. 20 plus 17 is 37. The column total, that is, let's see, that's 13 plus 17, that's 30. Oof, I don't know what the grand total is. Let's do that real quick. So 8 plus 12 plus 17 plus 17 plus 24 plus 8 plus 5 plus 12 plus 6. So 109. So 37 times 30 divided by 109. So this is about 10.183486. All right, here we go. Let's run our chi-square test. Chi-square test. Then we have a commercial. This is a long version of one. Sorry. Yeah. All right. So we are back to our problem. We have our chi-squared test. We have our observed, our expected, and they're going to fill in the expected, and now we just need to calculate. And there is our p-value. So let's write p-value is 0.0409, we'll say. And either way, looking at my alpha, this is way bigger than my alpha. Which means we are going to fail to reject. The null hypothesis. And that's going to tell us that there is not enough evidence to support the claim that the type of vitamin pill is dependent on the age of the person taking the pill. So we can conclude that the age and everything is the limit. So I want to take a look at matrix B. And you can see the 10.1 that I got over here for the 1-1. So kind of cool that it does all that work for you. All right. So let's do another one. I deliberately didn't put the fill in the matrices ahead of time because I wanted to show you how to do that since it's a new function for that. So before we get to the matrix and all that, let's do our null hypothesis. Let's read the question. A study of pet owners showed the following information concerning the ownership of dogs and cats. At alpha equals 0.05, is there a relationship between the number of people in a family and dog or cat ownership? Okay, so we can see that if there's one person in a family, how many of them had a dog, how many of them had a cat, and so on. And are these two ideas, dog or cat, versus number of people in a household, are those independent ideas or are they dependent? So our null hypothesis, pet ownership is independent of the number of people living in the household. This is not the claim. Versus our alternative hypothesis, which is pet ownership is dependent on the number of people living in a household. That, again, will be our claim. So let's put the data into our calculator again. So I'm going to go to second matrix. I'm going to edit matrix A again. And you'll notice this one is a 2 by 4, meaning 2 rows, 4 columns. Enter. And notice I'm just writing right over the old data. Quit out of that, and we're going to run a stat chi-squared test. So again, I put that into matrix A. It's going to calculate my expected value into matrix B. Let's see what we get. P-value. In this case is about 0.0581. And our alpha is 0.05. Ooh. Okay, so we're barely a little bit bigger than our alpha. All right, so what is our conclusion? We are again going to fail to reject. The null hypothesis because our p-value is bigger than our alpha. And so our summary is that there is not enough evidence to support the claim that pet ownership is dependent on the number of people living in that household. And that is test for independence. All right, so we are now on to the very last section. And this is right at the beginning of really advanced statistics. It's not going to be too advanced for us, but we're going to be doing one-way ANOVA. And ANOVA stands for analysis of variance. And I want to highlight, here's the AN for ANOVA of variance. So that's where the word ANOVA comes from, ANOVA, analysis of variance. So we are actually going to be using an F distribution. I have set it up so that we will see the F test statistic. We even have a way of calculating the F test statistic, but we are not going to use this information. An F table is, so far the only tables that we've had to use was the chi-squared, and it was one sheet. F tables are like many sheets, depending on the alpha and everything. It gets very complicated. So we're going to actually bypass the whole F distribution idea and just focus on p-value and alpha. So we're going to start with ANOVA. Is a method of testing the quality of 3 or more population means by analyzing their sample variances. All right. So our null hypothesis is always going to be, we're going to assume that mu sub 1 is equal to mu sub 2 is equal to mu sub 3 is equal to however many samples we're looking at here that we're trying to compare. The requirements, and then the alternative hypothesis is at least one mean is different from the other. I've seen some teachers go more into depth, because right after you can see that one is different, you can actually, there's a method that you can go in and identify which one is different. And then of course the real question is, why is it different? Which we won't get into any of it here. All right, populations have distributions that are approximately normal. Populations have the same variances or standard deviation. The samples are simple random samples of quantitative data, and they're independent of each other. And here's our test statistic. Again, I'm not going to dwell on the F portion of it, but what we are going to need to do, for example here, cell phone bills. The average local cell phone monthly bill is $50.07. A random sample of monthly bills from 3 different providers is listed below. At 5%, alpha equals 0.05, excuse me, is there a difference in mean bill amounts among providers? We're going to use the p-value method. Now, I have already put this into my list 1. This is my list 1, list 2, and list 3. You may need to take some time to clear out your lists and put those in, but I will show you just quickly. You can see at the top of my list is the 50, and then the 55, and the 58, and so on. So you may need, again, pause the video to put that data into there. We're going to state the hypothesis. We're going to assume that all 3 means are the same. So this is not the claim. At least one mean is different than the others. This is the claim. We're going to find the p-value, make a decision, and summarize our results. we are looking for, in our calculators, ANOVA, analysis of variance. So here we go. Stat, test, it's going to be all the way at the bottom. ANOVA. And then we have to list using the comma button. My comma button is right above my number 7. So I'm going to do list 1, comma, list 2, comma, list 3. And then I'm going to hit enter. And there's our F-test statistic, but we are not interested in that. We're interested in the p-value, 0.00239. And I'm going to note that that is definitely less than my alpha, which is 0.05. So we are going to reject the null hypothesis. Yep. The null hypothesis. So this means that there is enough evidence to support the claim that a difference in mean monthly cell phone bill amounts exists among these providers. So at least one of these means is different than the other, based on our analysis. Pretty cool. It's pretty cool we get to skip all the F stuff. All right. This data I have listed under my list 4, list 5, and list 6. I will show that to you. And you can see the 7.1, 7.4, 6.4, and so on. All right, now notice these lists lengths are different. The first one has 10 in it, the next one has 8, the other one has 9. That's totally fine. We have absolutely no issue with that at all. So let's set up our null hypothesis. Oh, let's read the question. The data found below measures the amounts of greenhouse gas emissions from 3 types of vehicles. The measurements are in tons per year, expressed as CO2 equivalents. Use a 0.05 significance level to test the claim that the different types of vehicle have the same mean amount of greenhouse gas emissions. Based on the results, does the type of vehicle appear to affect the amount of greenhouse gas emissions? So let's start with the mean of A is equal to the mean of B is equal to the mean of C, car C. And our alternative hypothesis is at least one mean is different from the others. All right. So I'm going to go on the assumption that you already put your lists into there, and I'm going to go ahead and run ANOVA again. Again, ANOVA. So stat tests all the way at the bottom of mine. Anyway, maybe yours is a little different. And we got another add. Okay. So mine is in list 4, list 5, and list 6. Maybe you rewrote yours in terms of list 1, 2, and 3. That's fine too. Just make sure you use the right one. And here is our p-value. Now, we got to be a little careful here. It kind of looks like my p-value is bigger than 1. It says 4.2969. But if you go a little bit further to the right, you have that E there with the -7. So let's interpret what that means. 4.2969 actually means times 10 to the -7th power. Here's what this actually means. 0.12345642969 is what this means. So you move that decimal point to the left 7 places and you get here. And in my opinion, this is about 0. And it most certainly is less than our alpha. So what's our conclusion? We're definitely going to reject the null hypothesis in this case. Which means we're going to support the alternative hypothesis. So we would say there is enough evidence to support the claim that at least one mean is different from the others. And that is ANOVA. Thank you very much. It's been an honor to do these series for you. Good luck.